Welcome to Cognito Key. Today, we're going to pull back the curtain on the tiny, invisible component that acts as the hidden heartbeat for pretty much every piece of technology you use. So, have you ever stopped to think about it? What gives your phone, your computer, or even your smartwatch its internal rhythm? What's that invisible pulse that keeps everything in perfect time? Well, the answer is this brilliant little circuit called an oscillator. You can think of it as the secret rhythm section for the whole orchestra of electronics. So let's dive in and see exactly what it does. Okay, so at its core, an oscillator is a circuit that does something that's, well, it's pretty magical. It takes that steady, direct current, DC, from a battery, and it transforms it into an alternating current, or AC. And that's this continuous, repeating, wave-like signal. That signal is the heartbeat we've been talking about.
Now, to really get how this works, you don't need to be an engineer. Forget complex diagrams. All we need is something we've all seen: a kid on a swing. Seriously, this simple analogy is going to make it all click.
Right, so at the very heart of the oscillator is something called a tank circuit. Now, this circuit is made up of just two main parts, a capacitor and an inductor. And the way these two dance together, it's a perfect mirror of that back and forth motion of a swing. First step, you've got the capacitor. Its job is to store energy. Think of it like pulling that swing all the way back right before you let go. All that potential energy is just sitting there waiting to be unleashed. And then, whoosh, the capacitor lets go and the inductor takes over. As the current flows, the inductor stores energy in a magnetic field. This is the swing at the very bottom of its arc, moving at its fastest. See? The energy has just transformed from potential to kinetic, and it's this constant back and forth between the two that creates the oscillation. Okay, but here's the thing, and it's a really important question. In the real world, what happens to that swing if no one is there to give it a push every once in a while? You got it. It slows down, and eventually it just stops, all because of friction. Now, in some perfect, ideal world, that swing would go on forever. We call that undamped oscillation. But back here in reality, circuits have resistance, which is basically the electronic version of friction. It makes the signal lose energy and fade out. And that's called damped oscillation. So how does the circuit fix this problem? How does it keep that swing going forever? Well, it needs a secret weapon, a perfectly timed push. And this is where the real genius of the oscillator circuit shines through. It uses an amplifier and this really clever technique called positive feedback. This is how it gives itself that tiny, perfectly timed push on every single cycle. It's just enough to cancel out the energy lost to resistance. And the process itself is just beautifully simple. As that wave of energy starts to weaken, the circuit basically grabs a tiny piece of it. It shoots that little piece through an amplifier to boost its strength, and then feeds it right back into the main circuit at the exact perfect moment. And that's what keeps the swing going. Now here's the really crucial part. That push can't be too strong and it can't be too weak. It has to be just right. There's a principle called the Barkhausen Criterion, and it basically says that the loop gain, which is pretty much the strength of that push, has to be exactly 1. That means the energy you add back is precisely equal to the energy you lost. It's the secret sauce for a perfect, stable oscillation. And that stability is why our digital devices are so incredibly reliable. So this really elegant solution is what makes oscillators so unbelievably useful. I mean, what are the big advantages that have put them inside practically every electronic device we own? Well, it really comes down to 4 key things. First, they are super cheap to make. Second, they have 0 moving parts, which makes them small, super reliable, and perfect for anything portable. Third, they're incredibly quiet. But maybe the biggest deal of all is that they can be designed to produce this massive, massive range of frequencies. And when I say a wide range, I'm not kidding. We really mean it. Oscillators are the reason we can have everything from your headphones all the way up to satellite communication. I mean, just take a look at this range. Audio-frequency oscillators, they operate in the range we can actually hear, so about 20 to 20,000 cycles a second. Then you jump up to radio-frequency oscillators, and we're talking millions of cycles per second. And then microwave oscillators? Well, they operate at billions of cycles every second. And to really put that into perspective, this chart shows you the scale. It's just incredible. If the entire range of human hearing is that tiny little bar on the left, then the frequency for radio is thousands of times faster.
And microwave frequency? It's thousands of times faster than that. The scale is just mind-boggling.
Let that sink in. Over 3 billion cycles every single second. That is the kind of incredible speed that powers our Wi-Fi, our GPS, and satellite communications. And it's all thanks to this humble little oscillator.
So, if there's one thing to take away from all this, it's that the oscillator is truly the hidden heartbeat of our modern world. It is that perfect swing, getting a tireless, perfectly balanced push. And it's that perfect balance that creates the stable, reliable rhythm that makes all our technology just work, day in and day out.
And that leaves us with a really fascinating thought to end on. If the oscillator is the rhythm section, creating the beat, then what part of the circuit is providing the sheet music? What tells that beat what to do?
Thank you so much for joining us here on Cognito Key today. If this explainer helps shed some light on the hidden world of oscillators, please do give it a like, share it with someone who might find it interesting, and of course, subscribe for more deep dives into the tech that shapes our world. See you next time.